This is the schematic diagram of my 10 MHz oscillator with 21 quartz crystals in parallel. It is from my previous video, nerds118, and in that video I measured phase noise and amplitude noise with my Linrad system, which is a direct conversion receiver, and also with the PN2060, which only can measure phase noise. And finally I compared the results with the results from an FSWP from Rode and Schwarz. And for phase noise, the three systems give very similar results. Minus 131 dBc per Hertz for the phase noise. The amplitude noise I could only measure with Linrad, and I got it at minus 134 dBc per Hertz, and the measurements were at 1 Hertz offset. An oscillator with a single crystal typically would give minus 120 dBc per Hertz. Assuming that all the noise comes from the crystals and that the noise is uncorrelated, which it of course is, one should expect a 13 dB improvement, which means minus 133 dBc per Hertz for the phase noise. In this video I will show the modifications I did to the oscillator to reach minus 133 dBc per Hertz at 1 Hertz offset. The old amplitude limiter, the stage here, with 4 FETs in parallel and with a very large source resistor in common for all of them, seems a bit ridiculous. I could have a single FET taking the current that I would get in this situation. But as it turned out, the phase noise became lower when I put more FETs in parallel. So for that reason and also other reasons, I think this amplitude limitation by saturating an amplifier is far from optimum. And it's also peculiar that I got better performance with this resistor here. I could have done it other ways. Anyway, I have changed this circuitry completely, and I have added one turn here. So I have in total 13 turns to get the voltage to the new limiter. That is to get a slightly higher signal level, of course. The new amplitude limiter uses the same amplifier as before with 4J310, but I changed the source resistor to 47 ohms to get much more power. And then the actual limiter is this JFET, which works as a resistor. When the amplitude on the drain of this main amplifier reaches a certain level, the rectified voltage from these diodes, they are Schottky diodes, as the voltage on the gate increases, at some point it comes near this voltage here, which is divided from 16 volts with these two resistors. And when this gate voltage approaches the source voltage, then this will be a resistor that loads the signal and brings down the level to the feedback output. This resistor here is selected to have the gain through the whole system at about 1 decibel. So the effect of this JFET is only to reduce the gain by about 1 decibel. I have collected average correlation spectra for over 25 hours with the new amplitude limiter. This is after 3 hours 10 minutes, and I placed the mouse at 1 Hertz offset and minus 133 dBc per Hertz. And then I step to the next screenshot, here and here and here. This is 25 hours, 43 minutes, and it seems the result is not quite minus 133, rather minus 132.5. I repeat, moving the camera a bit closer to the screen. This is 3 hours 10 minutes, 8 hours and 1 minute, 21 hours 35 minutes, and finally 25 hours 43 minutes. The PN2060 has been running in parallel. So here is the result after 3 hours 10 minutes, 8 hours 1 minute, 21 hours 35 minutes, and 25 hours 43 minutes. And you can see the result is fairly unstable, and it goes up and down. And once again, to see small differences in performance, Linrad has the option of calculating the average phase noise from about 0.4 Hertz offset to 1.5 Hertz offset. That number after 3 hours is average minus 131.8, and this is 871 averages. And I step forward 8 hours 131.76, 21 131.81, and 25 131.78. This gives a number for the performance that is accurate within something like plus minus 0.1 decibel only. The PN2060 has been running with a filter, a moving average over 19 points. Exactly how that is done, I don't know, but that is an option that makes the curve smooth here. Without the filter, the curve is much more noisy, as you can see. And there is one particular thing, just around 1 Hertz, it is not as noisy. And this means there is a noise signal coming from the device under test, my oscillator, and just around 1 Hertz. This looks like noise from the gate to drain capacitor, because this feedback that I have is maybe not exactly correct. The voltage, AC voltage on the source of the second transistor is not quite as high as the voltage on the gate. So I will try to change by making that voltage a bit bigger by taking it out from one more turn on the transformer. I will show the schematic diagram soon. But one more thing on this screen, I have changed Linrad to show the amplitude noise. And you can see here the white curve is very low. It is below 140 and it has not converged yet. There are blue points, which means that the imaginary part is negative. So the amplitude noise has become very much weaker. There is nearly no AM sideband noise anymore. And that indicates that the new amplitude limiter is much better than what I had before. Important to remember is this: average minus 131.78. There is a voltage drop from this gate to this source, mainly because this transformer is loaded by this resistor and also by this 270 ohm resistor through the low-pass filter that shifts the phase by 90 degrees. So to compensate for the voltage loss from here to here, I have taken the feedback to the drain at one turn more on the transformer. So it is 12 divided by 11 times the voltage on the source here, and that comes fairly close to the voltage I have on the gate. I have placed the mouse at minus 133 dBc per Hertz and 1 Hertz offset. This is after 2 hours and 6 minutes, and here is 4 hours and 4 minutes, and this is 15 hours and 48 minutes, and finally 24 hours and 32 minutes. And it looks like the level at 1 Hertz offset now is about minus 133 dBc per Hertz. The PN2060 with the filter moving average with width equals 19 shows minus 133.7 at 2 hours, and at 4 hours it says minus 134, and 15 hours minus 134 again, and 24 and a half hours minus 133.6. So it shows something a little bit better, but the curve form here shows that something is not good, and I think this is just statistics. The average from 0.45 up to 1.5 Hertz offset develops like this. You can see in this window how it changes over a short range of averages from 559 to 581. It varies a little bit, but this is only 2 hours. So if I step further, the value is more constant. This is 4 hours, 15 hours, and 24 and a half hours. And it looks like minus 132.51. And before I made the change, it was 131.78, so there is a significant improvement. The unfiltered spectrum in the PN2060 looks like this after 4 hours, and this is 15 hours. And look in this region, the noisiness is not very different here as compared to the surrounding points. And this is 21 hours, and the extra noise I saw here is much smaller. It looks a little bit smoother, just around 1 Hertz. And 24 hours, this is even more visible. So there is still a contribution of noise from the gate to drain capacitance. I have modified the unit like this, just changing the number of turns on this transformer. For the signal going to the drain, being 2 turns up, a total 13, and then the signal to the amplitude limiter, further 2 turns up, so it's now at 15 turns. The mouse is again at minus 133 dBc per Hertz and 1 Hertz offset. And I step through the screen dumps I made. This is 2 hours 22 minutes, 3 hours 56 minutes, 6 hours 9 minutes, 10 hours 31 minutes, 15 hours, 24 hours 39 minutes. So it looks like minus 133. The PN2060 shows something a little better, minus 133.2 after 2 hours and 22 minutes. And minus 136 at 3 hours 56 minutes, and then minus 134 at 6 hours, 133.8 at 10 hours, 134.1 at 15 hours and 133.2 at 24 hours and 39 minutes, which was the longest time I made this. When I look at the average from 0.45 to 1.5 Hz offset from the carrier, it starts at minus 131.8, which is not quite as good as expected. And then when I step on, it improves. This is 3 hours and 56 minutes. And it seems to stop here. This is 6 hours, 10 hours, 15 and 24. So 132.6. And this is a bit better than I had before. Not much, but I think it is significant. When I step through the unfiltered spectra from PM 2060, this is 2 hours, 3 hours 50 minutes, 6 hours, 10 hours, 15 and 24. We can see that the noisiness of this curve seems to be closely the same over the entire frequency range. And that seems to indicate that the variations of the gate-to-drain capacitance due to noise in the transistor is well compensated now. I have added an amplifier now. It's a Norton amplifier designed to give 50 ohms output impedance. The output is 40 milliwatts, or at least it was 40 milliwatts when I measured it some time earlier. I may have changed something, so I will check that. This is what the unit looks like inside. The cable you can see from here to here. That's a small capacitor I added to get the frequency where I want it. I don't have small polystyrene capacitors of good quality. And, well, it looks messy, and it is messy. I made many various things here which I have not talked about. And there are unused components, like some of the inductors. This one and that one are not used anymore. I step through the screen dumps with the mouse at minus 133 dBc per Hertz at 1 Hertz offset. This is 2 hours 46 minutes, 4 hours 37 minutes, 10 hours 56 minutes, 13 hours 59 minutes, 23 hours, 31 hours 18 minutes, and 37 hours 44 minutes, and finally 48 hours 42 minutes. And it is a little better than minus 133 dBc per Hertz at 1 Hertz offset. And here are the PM 2060 results, filtered with the moving average filter of width 19. 2 hours 46 minutes, 4 hours 37, 10 hours 56, 13 hours 59, 23 hours 9, 31 hours 18, 37 hours 44, and finally 48 hours 42. The result here is minus 133.3, very close to what I found in Linrad, a little bit below minus 133. So after 48 hours, the difference between the two measurements is small. And I repeat, you can see there is big differences in the beginning. This is only 10 hours. And then it becomes, 23 hours. It differs by a whole dB from the result 48 hours. Then it was here. So if I would wait another couple of days, they would converge, but I don't want to do that. Now I step through the unfiltered curves from the PN 2060. And here is 48 hours. And at this very long time we can start to see the curve is smoother around 1 Hertz than it is far away on both sides. But the difference is not very big anymore. In the region 1 to 10 Hertz, there are 7,092 averages. The average from 0.45 to 1.5 Hertz offset is similar to before. Here is 2 hours, and I step through the other times. And you can see it varies, but it converges a little bit. Here is 48 hours, and it has reached minus 132.55. And that is with the amplifier also added. And before I saw minus 132.63, and the difference is insignificant. I will now go through the characteristics of this amplifier and oscillator. To begin with, I have to check the calibration of my network analyzer. So I have open, short, and the reference load 49.9 ohms. This is with nothing connected, and now I connect open, and it changes a little bit. Now it shows 1.4 pf, and with nothing connected it showed 175 microhenries. That's close enough, so I don't worry about this. And then I connect short, and this shows 76 milliohms, close enough to 0. And my reference load 49.97, well, close enough to 50, although it really is 49.9. But precision is good enough with a good margin. The connection from the amplitude limiter, which is here, goes through this cable to the input, which is here. Therefore, the calibration for transmission is done with this cable inserted with a very similar length. And we can see that the amplitude is correctly calibrated, 0 dB loss, and more importantly, the phase angle is very close to 0. If I omit that little extra cable, the phase is 3 degrees, and that isn't really significant, but just out of orthodoxy I have included it. For power measurement I'm using the oscilloscope. That's the best instrument I have for power measurements. I'm checking the input impedance of the oscilloscope, and it's very close to 50 ohms, as you can see here. I have connected the oscillator. As you can see, it gives 4.2 volts peak to peak into 50 ohms. The overtone content is small, so I don't have to think about that. when computing the power from the peak-to-peak voltage. And the power indicated by the spectrum analyzer is 16.3 or 16.25 perhaps. This is in perfect agreement with the measurement with the oscilloscope, 16.4, because the cable attenuation from the box all the way up to the spectrum analyzer is about 0.1 dB. I checked the output with the oscilloscope probe. It shows 4.1 rather than 4.2, so the accuracy is pretty good. But I can still take this into account. I can measure the current through the crystals with this current probe. It says 1 milliamp per millivolt. This means that the total current through all the crystals is 50 milliamps peak to peak. That means 17.7 milliamps RMS, 0.84 per crystal, and that is about 50 microwatts because the resistance in the crystals is about 70 ohms. I have disconnected the feedback. Now the unit is a selective amplifier. Here is the output impedance, very close to 50 ohms, but one can see there is some small interaction with the crystals. I changed the scale by a factor of 10, and you can see here it is about 2 ohms that differs from the center frequency to off the center frequency. The input impedance is 52 ohms on the resonance frequency and 57 ohms off resonance. And of course at both sides. The gain through the unit is 2.4 decibels. Here, when I'm running at a low level, minus 10 dBm on the input, and the Q is 1.13 million. The phase shift is very close to 0, 0.3 degrees only. All the performance tests have fallen out fine. The variation of the input impedance on the frequency of resonance, I have 57 ohms, that is what I have outside, in parallel with the impedance of the crystals. So I can compute X, it's 592 ohms, and the voltage, I know 2.4 volts peak to peak. This gives me 58 microwatts per crystal, and that is close enough to the 50 microwatt I found by assuming 70 ohms. I forgot to show the 48-hour screen dump of amplitude noise in Linrad. Here it is. At 1 Hz offset it is well below minus 148 dBc per Hertz. 10 Hz offset below minus 155. And I don't know where it really is, but it is very low. Another thing, there are sometimes glitches. You can see one here in the baseband graph. It is caused by this frequency jump in the channel 1 reference oscillator here. There was a similar event here. It is something I didn't show before. But when I look at the frequency versus time, it looks like this, and you have an abrupt frequency change here. It's only in channel 1, so it doesn't affect the correlation spectrum much, because it's not present in the channel 2 at the same time. Nevertheless, it degrades the signal-to-noise ratio of the measurement a little, particularly at fairly wide separations compared to the normal fluctuations of the frequency, which are very slow. This event creates frequencies that extend to at least 1 Hertz offset, as you can see here. The channel 1 oscillator has 2 tunable capacitors. I think maybe they could be the cause of the problem, so I will try to clean them. They are this kind of capacitors, and I have had problems with them in the past. I am using isopropylic alcohol and cotton pins for cleaning. And you might see there is some gray area on the cotton after my doing this many times. And these cotton pins are for the fixed part of the capacitor. And obviously there has been a contact problem in this capacitor. The other capacitor looks worse. You can see the cotton is dark here. So I go on several times. And it gets dirty. Cleaning the fixed part clearly made a difference. Cleaning it a second time made a very small difference, but yet I can see the dirt on the cotton here. I have collected correlation spectra for 21 hours now and made a time-lapse video during most of that time, so I can see if there have been any glitches or problems in the waterfalls. The phase noise now, after 21 hours 42 minutes, here is minus 133 dBc per Hertz, just as expected. I'm using Avidemux. The time-lapse video lasts 13 minutes, 36 seconds, and I have looked through it all, and it looks like this for the phase noise and like this for the frequency. But I don't want to play all of it here, of course. I have made a speeded up version which lasts only 1 minute 20 seconds. And it looks like this. And here one can catch the worst events. Towards the end there is something horrible happening. You can see how the green trace is lifting while the yellow trace is unaffected, because it happens only in channel 1. So this happens as soon as the amplitude of the signal is changed. The big event starts here. When I step 1 frame at a time, I can see that channel 1 had something dramatic. I step 1 backwards, and it's only the noise floor that has changed, The peaks look the same. I step through the worst section of this event and look at the noise floor here when it comes. And you can see it here also in the noise floor. But it's fairly wideband, and we have this characteristic thing at the center also. Note that the numbers here become red at some point when Linrad thinks this is too much, do not include it. And you see that there wasn't much change on the green trace. But when the interference is a little bit slower, then the green trace goes up. Note that the noise floor is lifted by typically something like 30 decibels close to the carrier. And sometimes Linrad doesn't use that data for collecting averages. Sometimes this routine fails. It is not cleverly designed. Here you can see the notch at the center, because there are some capacitors in the sound card. It's not DC coupled, it's AC coupled, and you can see it is very sharp, this notch. And it's also visible here in the waterfall. Although there has been an ugly event, here the frequency dropped, stayed low for a while, and then jumped back up. And the step is in the order of 0.2 millihertz. Here it seems two different events happened close in time. First this thing, which didn't affect the AD converter, and then this, which was much more distinct and changed the level on the sound card. There are a great many BNC connectors in the system. And finally the sound card. I will not try to fix this problem now, because it doesn't affect the measurement. I have minus 133 dBc per hertz, and I think that is accurate, and it is in agreement with expectations. When looking at other offset frequencies than 1 hertz, this is a measurement of 48 hours, but without any filtering. So this is minus 133, and 10 hertz would be probably close to where the marker is. That's minus 163. And then at 100 hertz, very difficult to say. Probably it is smoothing out towards the flat here. And what happens at here, I don't know. Then this measurement says minus 186 for the flat noise floor at large offsets. But that is questionable. So low noise levels with this method have problems. They may be very sensitive to the impedance matching, because one is measuring the excess noise, not the absolute noise. And that is the noise difference between a dummy load and what comes from the device under test. And mismatch can change that result significantly and make it completely wrong. I think for the device under test now, with 44 milliwatts of power, it has a power level at large separations for the noise floor that is high enough above room temperature to make mismatch errors less important. But I will do a different type of measurement to establish with certainty where the flat noise floor actually is. This is the noise head of my noise figure meter. It provides a noise level that is 3 decibels above the value that is presented on the reading on the instrument. So when I set it on 0, it produces a noise signal that is 3 decibels above room temperature. And if I put it at some other reading, I get an extra noise of 3 decibels. This means that I have a precision source of dBm per hertz. I verify that the impedance of that noise source is very close to 50 ohms. To measure noise levels, I use this pair-sieves preceded by 2 preamplifiers and in front of them a matchbox. Then I will measure and tune the impedance at the input of those units, that's here. And it is properly tuned. It's off by 1 ohm on the imaginary part. And that's close enough. The feedback is disconnected and my multi-crystal box is now a selective amplifier. I have put a 50 ohm dummy load on the input and now I'm looking at the output and I have set the frequency in the pair-sieves to match the center frequency of the crystals. And as you can see, there is a noise peak with some width of about 10 hertz or so. And I have this S-meter graph and I can read the noise level here. And it is minus 68.37 in arbitrary units. Now I will connect instead the noise head. And this will take quite some time because this is a slow process because the Fourier transforms are very large. So now it is just a 50 ohm dummy load that is connected because I have no current in the noise head yet. The noise level now is about 18 decibels lower. I set the noise figure meter to 15 decibels. It's in the high range, means that I am 18 decibels above room temperature. And it's drifting slightly, so I adjust it again to 15. The noise level now, minus 174, plus 18, 15 plus 3, gives minus 156 dBm per hertz. And I wait for a while to see what the readout will be. A noise level of minus 156 dBm per hertz gives here minus 76.31 dB on the arbitrary scale. The noise levels I measured here and here include the noise of the receiver, which is down here, but it is more than 10 decibels below these values, so the influence is less than 0.1 decibel, so I ignore that. Here is what I see. The level at the center was minus 68 something, and for the noise figure meter, when it was set to 15, was minus 76 something, and the difference is 8 dB. And that means that the noise at the center is 8 dB above minus 156. And then the carrier is 44 milliwatts, 16.4 dBm. So I arrive at the phase noise at the center of minus 167 dBc per Hertz. I got for the total noise 3 dB more, because half of it is amplitude noise and half of it is phase noise. This is just white noise and there is no carrier for it to be correlated to. The definition of Q is frequency over bandwidth, which means that bandwidth is frequency over Q. 10 MHz divided by 1 million means 10. This is the AI result when I ask for the transmission through an LC filter as function of some fractions of the bandwidth. And the LC filter should have the same shape as the crystal filter. And I'm interested in transmission at 0.1 bandwidth, which means plus minus 1 Hertz. And I see 0.9806. Then I ask how the gain is influenced when I apply positive feedback with a feedback of 0.9806 times. And the open loop gain is exactly 1.0. Because that it is, because it's oscillating with a constant amplitude at the center frequency. And then I get the answer here 51 times in amplitude. This means that the phase noise I see, minus 167, will be degraded by 34 dB when I apply feedback. And that should give me minus 133 dBc per Hertz. And that's exactly what I have observed, which surprises me because I had expected some other phenomena also, but seems not so. The noise at minus 167, that is the thermal noise of the crystals, because when I feed the amplifier from 50 ohms, the noise is much lower than what it is when I feed it with the crystal. To see the flat noise floor at a large separation, I have set the frequency to 10.7 MHz for reasons that will soon be obvious. The level I see here is minus 53.8. I have now disconnected the device under test. From where the mouse is now until here, I had nothing connected, and from where the mouse is now and continuing on, I have the noise head connected. I will now set current until I reach the same level as I had before. It's about here. .3, half a decibel. Oops. Oh, the wrong direction. Well, from here to here. 53.8 or 53.79. Well, one more time. 53.78. That's close enough to 53.82. Noise figure meter 9.5. It means that the noise is 12.5 decibel above room temperature. So this is what I find. The noise at 10.7 MHz is minus 161.5 dBm per Hertz. And with the carrier at 16.4 dBm, that gives noise at minus 178 dBc per Hertz. And that's amplitude noise plus phase noise. So the phase noise is at minus 181 dBc per Hertz. Here I have a crystal filter at 10.7 MHz, and after that is a stop filter that stops 10 MHz and presents a high impedance to the first filter. So I send a signal in now in this port, and it is directly connected to the other, so it goes further here, and there is a dummy load. And in this port I can take out 10.7 MHz. And here is the output at 10.7 MHz. The loss is 0.8 dB about, so the loss is small. Now I put the dummy load at the 10.7 MHz port and looking with the network analyzer at the output for 10 MHz. And I have set the network analyzer to 10 MHz, and here the loss is 0.2 decibels. I had to set 20 decibels of attenuation for the perceives now that I have two preamplifiers in front of it. This should not have changed the input impedance to the first preamplifier, however. So now I'm looking at 10 MHz in the output where I should have the 10.7. Here is the noise at 10.7 MHz. And I can have a fairly large bandwidth, so this doesn't take much time. And this is the reading I get. At the same time, I have 4.14 volts on the 10 MHz output. Now I stop oscillations by putting a short on the feedback output. Like that. This caused a spike at 10.7, but not very strong, because the oscillations stopped gradually. So I wait until I can see the entire trace to see if there is any difference. The noise may have increased slightly if there is some compression in the amplifiers. Now minus 70.11, it was minus 70.25 before. So the difference is 0.15 decibels. And I can ignore that. There is not a significant compression through the amplifier. And that is what I thought would be the case. So I can say the phase noise is minus 181 dBc per hertz. The PN2060 gives minus 184. That's where the mouse is now. I can disable the spur removal, and this does not make any difference at this frequency. And I put it back, and then I can enable filtering. And it still shows minus 184. The specifications for the PN2060 is that it should be better than minus 180 dBc per hertz, above 100 kHz offset. As you have seen, the short time stability of this oscillator is extremely good, minus 133 dBc per hertz. That's about 10 decibels better than any other crystal oscillator that I have seen on the internet. But the long time stability is poor, really bad, because only the crystals are in a thermostat. The rest of the components are at some elevated temperature above room temperature. The temperature probe here shows now 37.8 degrees. I will switch on this fan to make the temperature go down a little bit. The temperature is stable now, 6.8 degrees below what it was before I started the fan. And the frequency has drifted by about 60 millihertz, 0.06 hertz at 10 megahertz. Not much, but for a high stability oscillator, this is of course unacceptable. It would require a thermostat for everything, not only for the crystals. And reasonably 2 thermostats, because the crystals want to operate at about 85 degrees, and that is too much for polystyrene capacitors, I think, in the long run. The time to reach equilibrium was about 1 division, and that is 1,000 seconds. So frequency drift is very slow. Another issue for long-time stability is the supply voltage. It is now 16.03, and I increase it. The primary voltage is 25. I increase that by 1, 2, 3, 4, 5, 0.5 volts. And this will take quite some time, because I have an RC filter with very large capacitor and a large resistor. That's why I had 25 volts. If I remember correctly, the capacitor is 1.6 farads and the resistor is 20 ohms. And as you can see, now it is up by 40 millihertz. And I have set the time scale 10 times faster as compared to looking at the temperature sensitivity. Now I have a stable supply voltage, almost 0.4 volts higher than before. And the frequency change is about 40 millihertz. Slightly more than that. I can feed the unit directly from this supposedly low noise power supply. Already after 5 minutes, I see the noise at 1 hertz here is about minus 118 dBc per hertz. And I look for the amplitude noise, and it is not converged completely yet, but it is very much higher than before. Something like minus 125 or so. And not unexpected, amplitude noise and phase noise are strongly correlated. Both are caused by a varying supply voltage. And it's the real part, the white trace, that is strongest. It means that when the frequency is at maximum, the amplitude is at maximum or minimum at the same time. The strong correlation between amplitude and phase noise is also seen here. You can see the noise is much stronger on one side as compared to the other, because with AM modulation, sidebands are in phase, and in frequency modulation they are out of phase. So they add on one side and subtract on the other. With an appropriate thermostat for everything inside this box, and for a high stability power supply also, this oscillator should give a more predictable long time drift than what we have with just a single crystal, because the frequency drift over time would be the average of 21 crystals.